Let's solve a very basic Pwnable challenge. In this video, we will host the challenge with Docker and also write and run our exploit in a Docker container, as well as get a first introduction to Pwn tools, an awesome Python library for developing exploits. You can find the Git repository with the challenge on my GitHub called Pwn Docker example. If you have questions or issues, check out the README of the repository. I will keep updating it with information. So let's get going. I'm using here my Mac to show that with this Docker workflow, it's easy to do Linux binary exploitation on a Mac, but it should work the same way on Linux and hopefully also on Windows. Anyway, first we clone the repository. Here we find two folders, the challenge and the CTF folder. Let's first start the challenge server. We do this by building the Docker image for this challenge first. The command is in the Docker file at the top. This will take a moment. In the meantime, we can also build the CTF container. I introduced both these Docker containers in an introduction video about Docker. I also will link it below. The CTF container is a pretty shitty image I came up with. It's nothing special, but it's good enough to run and develop our exploit. It should be noted that both Docker containers are based on the same Ubuntu version. This is very useful for binary exploitation challenges because many exploits depend on, for example, knowing the exact version of some library like libc. So if you know the version of the challenge server, it's a good idea to mirror that locally. Often you can also take a guess and assume it's the latest stable or LTS version of Ubuntu. That seems to work generally well. But maybe it's also part of the challenge to figure that out through vulnerabilities that allow you to leak data. Anyway, in this case, here you don't need to worry about any of that, the version matches. When the images are built, you can run the containers. The command is also in the Docker files. But make sure that you are in the correct location when you run the CTF container because it mounts the current folder into it and we want to make sure we have access to the challenge binary. And so I'm here in the Pwn Docker example parent directory, which will then be available inside the container too. Both are running now and we can use netcat to speak over the network with the challenge binary. If you are curious and want to see this network communication, install Wireshark. Listen on the correct interface and filter for TCP packets on port 1024 and you will see the text being sent back and forth. Anyway, not important. Now we are ready to tackle this challenge. Let's see what we have been given. We have here the system health check binary and the source code. Source code is given because it's a basic Pwnable challenge, it's not a reversing challenge. But it's good practice to reverse it without the source code, and so feel free to do that. And then you can peek into the sources to check if you did it correctly. But I'm lazy, let's look at code. At the top you can find information on how this binary was compiled. We are especially interested in the flags that disabled some security protections. No PIE, position independent code, which means the binary itself runs without ASLR, at least the code and data section from this binary. It doesn't affect loaded libraries like libc, the heap or the stack. Those are still affected by system ASLR. And we have no stack protector, which means there is no stack cookie and stack-based buffer overflows are easy. Inside the container you can also use the tool checksec on the binary to see the enabled security features. And you can also see that no stack canary, stack protector was found and the position independent code is disabled. But NX is enabled, so non-executable stack, which means you can't use shellcode like in old buffer overflow tutorials because the shellcode on the stack couldn't be executed as code. At the end of the video I have a few general tips and resources to learn what that all means, so make sure to don't miss that. Now back to the sources. So first of all, you can see here a few functions named ignore me. They are just here to set up the binary so it runs nicely. It doesn't have to do anything with the challenge and can safely be ignored. Here it disables buffering on the input and output and we register a signal that will kill the process after 60 seconds, which helps us cleaning up long-hanging processes. Ignore them, they are just setup stuff. That's why they are named ignore me, but feel free to research what these functions do. Anyway. Here's the actual part of the challenge. We have a function backdoor, that's obviously super suspicious, and then this remote system health check. In the main function, we see that this function is called. What does it do? Well, it simply asks you to enter a password, The password is statically stored in the binary here, super secret password. It does a string compare on your input, and if it's correct, it will execute the top command to give you some system information. If the password was wrong, the program exits directly. If you have done some basic exploitation challenges before, you might immediately notice the call to gets, which reads in a string into the buffer passed as a parameter, but doesn't check the size. So if you enter more than hex FF characters, so 256, it will overflow this buffer. This buffer is stored on the stack, and on the stack there is other critical data which can be overwritten. A very important piece of critical data is the so-called return pointer. So what exactly is that? When a C program calls a function, it is compiled to an assembler call instruction. The call instruction places the address of the next instruction onto the stack and then jumps to the code of the function. When that function is done, it will execute the read instruction. This read instruction looks at the value on the stack and jumps there. So then the execution can continue. By the way, these graphics are from my binary exploitation playlist episode hex C. If it's unclear, try to watch the series. So this value previously pushed by call onto the stack decides where we return to. Which means when we can overwrite this value which was placed by the call instruction on the stack, for example due to a buffer overflow, we can override it with a value of our choice and decide where we jump to when the function tries to return. But let's go slow. First, let's see what happens when we enter the password. We use netcat to connect to the server, enter the password, and we see the output from the top command. Cool. Now let's see what happens when we try to overflow the buffer. Let's simply enter a lot of A's, trying to overflow it. But we have a problem. Wrong password, nothing happened. The problem is that in the case of a wrong password, the function never tries to return, we simply exit. So we can only reach the return with the correct password. But how can we overflow the buffer and at the same time enter the correct password, which is super short? We will get back to it in a moment. Let's start preparing our exploit script. I'm using here VS Code and I create a new asd.py script in the folder that is shared with the CTF container. In most of my videos, I'm not using Pwnable because it's kind of fancy and magic, and I prefer to show how to implement stuff yourself, rather than using too many abstraction tools. But maybe it's time to move forward and we have done stuff by hand for years. So, from pwn import star. The documentation also has various examples and some details. Definitely check that out or look for other example exploit scripts using it to steal snippets. So let's start by simply launching a new process and we execute the binary directly, so we don't use the network to call to the actual challenge server yet. And then we call receiveLine to get the first line of output from this process and print it. It should be noted that I don't have Pwnable installed on my host machine, but it's available inside the container, so we can use this Visual Studio Code shell down here to use docker exec to get into the container. Go to the folder where the script is stored and we can execute it. It started the local process, printed the first line asking for password and exited again. We can also use sendLine to send the password as input to the process, and at the end we can use interactive. Let's quickly comment out the password again. Interactive simply gives us an interactive input-output shell, like netcat. So when we run it, you see the red prompt here and we can enter the password ourselves, and that worked. So basically, if we successfully execute an exploit that gives us a shell, we want to use interactive to send inputs to the new shell comfortably. But before that, we need to send our exploit input. So what's the trick here to trigger the buffer overflow? Well, if you have some experience with C programming, then you might know strings in C are null terminated. Meaning, in memory, there is no information about how long a string is. A string is simply defined as any sequence of characters and it stops at a null byte. So string compare compares strings, which means if it reaches a null byte, it is done. Alright, gets on the other hand can be a bit confusing because it says get a string from standard input, but if you read the actual description, it says reads a line from standard input, which means it reads into the buffer until either a terminating new line or end of file is reached. There's a discrepancy between the string compare and gets. So gets absolutely can read null bytes from the input, it only stops at new lines, while string compare reads new lines but stops at null bytes. Now let's send a lot of characters trying to provoke the buffer overflow. I'm using cyclic here, which is a function by Pwnable which creates a unique pattern string. This becomes useful in a moment. I'm creating a string that is hex ff long and a bit more just to be sure. When we execute it now, we see that a code dump appeared in the folder, indicating that a process crashed, and our interactive shell got an end of file, and also we see that the binary stopped with a zigzag, so a segmentation fault. Let's investigate. To do that, I'm adding a small pause to the script. Raw input is typically to get user input in the console, but I'm simply using it to wait until I hit enter. I want to use this to attach GDB in the meantime to the process. Pwnable has some fancy GDB attach integrations, but to be honest, no clue how that works and how I would maybe set that up here in Docker. If anybody knows some cool tricks with that, please write it in the comments. Anyway, let's execute it. The script is now waiting for input. In the meantime, we can open another shell inside the container, and with gdb-p we can attach to the running challenge process. We need the PID, so PID of the process name system health check will give us that. There we go, we are attached. The process currently is waiting in the read for user input for the password. And we continue the process. Then we go back to our script, hit enter, which then continues and sends the password with the long cyclic pattern. Let's go to GDB. Oh, that doesn't look like it worked. The problem is that with the system function, we spawned a new child process and GDB followed that new process. Detaching parent process, you can also see here it executed top. That's not what we want. We want to stay in the parent process. Let's do it again. Attach with GDB, but this time set the follow fork mode to parent, and then we continue. Let's send our payload now. Hit enter. There we go. The parent crashed in a segmentation fault. As you can see, this is a very colorful GDB. Looks a lot more fancy than plain GDB. That's because I have installed the Pwnable GDB extension in the CTF container. So if you use all that Docker setup, you have that too. So here are the registers. Here's the disassembly, which right now only shows the return instruction where we crashed. We see the stack and the call stack or backtrace. The colors also help you quickly identify what the numbers could mean. So yellow values look like valid stack addresses, red values look like valid code addresses, and white is just basic data. And so, as I mentioned earlier, the return instruction takes the address where to return to from the stack. RSP points to the top of the stack. You can see the stack also displayed here. RSP points here. Pwnable already recognized that the values on the stack look like a string, so it didn't display raw numbers like here, but displayed it as a string. And this is the cyclic pattern that the cyclic function generated. Let's take a few of these characters, because with that we can calculate the offset. How many characters do we need until we reach this point on the stack? But before we do that, let's make this all a bit more comfortable. We can create a .gdb init file and add the set follow fork mode parent. When we now execute GDB, it attempts to read this as an init file. However, it complains because we need to allow it to be loaded from anywhere, so we need to add this autoload save path line in our home folders root gdb init. Anyway, now we don't have to type that in every time when we want to attach GDB, it will be automatically executed. So from the Pwnable docs, we can also learn about cyclic find function. It calculates the position of a substring into the sequence. So we can create a padding to fill up the buffer until we reach the return point on the stack. We repeat A so much to reach the location where we found the ACLAACMA string. And the next 8 bytes will now override the return pointer. I call it in my script RIP, like the instruction pointer register, because essentially it's the 8 bytes that controls it. The return instruction takes this value from the stack and sets RIP to it. That's all the return instruction does. So for me, the ret instruction is not really a return, it's rather set RIP to whatever is on the stack. Anyway, what do we want to set RIP to? As a first test, let's just use a recognizable number. P64 is another helper function from Pwnable, which simply converts this integer number into an 8-byte, 64-bit raw byte string. So we can send the string as input to the program. and we use hex 424242, 434343, so this is CCCCBBBB. And don't forget to add RIP after the padding, and then let's try it. Boom, there we go. On the stack we can see the string CCCCBBBB, and you can also see in the disassembly that return attempted to jump to this address. Obviously, still a bad address, thus we have a seg fault. So, where do we want to jump to? If we look back into the challenge source code, we might remember the backdoor function, which simply should execute a shell for us. So how about we simply jump to that snippet of code and reuse it? With pbackdoor, we print the symbol backdoor and find the address of it. We could also disassemble this function to find the address. So this is the start of the backdoor function. How about we try to jump there? Hex 401254, replace that and try it. Attach GDB just to make sure, continue, boom! Crap, we got another seg fault. But look, where? In the backtrace you see that we were coming from the backdoor function. So we successfully redirected code execution into the backdoor function. This is awesome, we basically won. We just run into some weird other issue. And this one is inside of do's system, so inside the libc library function system. How does that make sense? How can a widely used library like libc crash so easily? Well, if you are desperate, you might just search for the assembly snippet that caused it. If it happens in a popular library, it might be a known issue, right? And indeed, you can learn that moveApps instruction doesn't like it when addresses are unaligned. Calling an SSE instruction moveApps with unaligned parameter causes a crash. So let's look at this instruction. It references RSP, the stack pointer, and the stack pointer ends in an 8. This is a problem. Because we jump to this system function from this buffer overflow, everything is messed up. The system function expects that the compiler makes sure the addresses are 16-bit aligned, and that means we want a 0 at the end. So how could we do that? Somehow we must change the stack pointer before we call into system. So what kind of stuff affects the stack pointer? Think logically. Any push instruction moves the stack up, and pop instruction moves the stack pointer down. But also any call instruction places a new value on the stack, it's like a push, and any return instruction takes a value from the stack, so like a pop. So what if we execute a second return before we go into backdoor? We simply could use the first return of our original function and override the stack value with the address of another return instruction. This means after the first read, it will jump there and now execute that return. And this return takes the next value from the stack to continue execution there. This, by the way, is a tiny ROP chain, return-oriented programming. Anyway, this way we can easily move the stack pointer one element further and thus align the address of the stack pointer. So let's look for a return instruction. I simply use object dump -d to get the disassembly of the whole binary and then grep for red. So any of these addresses point to a return instruction. So let's add that to our exploit. The first address we jump to is the other return instruction, and after that we jump to the address of the backdoor function. Let's try it out. Let's change the exploit script from launching a local process to connect to the remote challenge server. In this case, this is my local IP. This is why PwnTools is so awesome. We can easily switch between a local process and the remote server. The functions to talk to it stay the same. Let's run it. We get the output of top. Now let's see if we have a shell. There we go, looks good. And we can read the flag. Awesome. This was obviously a very quick walkthrough, a lot to take in. Not going into a lot of details. And it will be hard to apply these steps to some slightly different exploitation challenge. There are a lot of small pitfalls and different exploitation strategies, and as soon as other mitigations like ASLR and stack cookies are turned on, it gets more difficult. There is no magical spell to quickly explain that, so it will take time and you will have to rewatch videos or read different write-ups. I encourage you to take a lot of notes and just try it. I have a whole binary exploitation playlist covering challenges from exploit education, but it's 32-bit and a bit old. A lot of the challenges are solved with shellcodes, which are rarely a thing on 64-bit Pwnable challenges due to the non-executable stack. But regardless, many of the concepts are still the same. It's still very useful to watch it. Maybe also check out the Exploit Education Phoenix challenges for 64-bit and practice with them. Don't be scared to look up write-ups for those too, and also watch my recent videos where I give general tips on how to avoid some annoying pitfalls. I'll link everything below and on GitHub.